physicist, experimental physicist. He made his PhD in Stuttgart, in the Max Planck Institute. And after that, he moved to Grenoble, and later he came to the campus, to the ICMM, where he obtained a Ramonica Hall grant and at the same time an NiPS₃ grant. So, close. Okay. And now he is an expert in electronic transport and electronic properties of nanosystem, and also has worked in heat transfer in this material. And now I think basically, now at least I found very interesting the work he's doing in the coupling between semiconductor and superconductor in order to obtain qubits. He has an extensive list of publications with a lot of impact. I have to say also that he collaborates with people in the theory group of this institute and also with Paloma Tejedor in the experimental part. And that is no more. So today he's going to entertain us with this title and this seminar. Okay, thank you very much.
Good morning, everyone, and thanks, Luis, for the invitation. So it's a great pleasure to present some of our recent work. I have given seminars here before when I had just arrived, and at that time we didn't have a lab, so I also didn't have results produced here. So it's nice to come here and show the results that we have been doing the past years. So as the title of my talk, I put hybrid superconducting devices from transport to quantum devices. Here, what I will try to do is to showcase a bit of the activities we have in our group, the different material platforms, and the different activities, and they surround this kind of thematic, so superconducting devices or hybrid devices. And the motivation for this, starts really with the importance of superconducting devices on technologies, or as we would say, nowadays, quantum technologies. So I put here some examples, and the main examples I put here are based on this key ingredient, which is the Josephson junction, right? So this is really an effect that was predicted already decades ago, but that has gained a lot of importance in applications in quantum computing, quantum sensing. So on the one hand, I put here really going from the Josephson junction and now to quantum processors. There have been several beautiful developments in the last decades, like the observation of macroscopic quantum effects in superconducting circuits, which has won the Nobel Prize last year. And this has led to these lines of research of superconducting quantum circuits and to the point where we are at noise intermediate scale processors. On the other hand, also, this same ingredient can be used for other applications. So one notable one is this so-called superconducting quantum interference devices, which are very sensible magnetometers, so they're used for quantum sensing. But there are more applications in quantum technology, so I also put here, for instance, single photon detectors that are based on superconducting nanowires. So as you can see, there are quite a lot of activity in terms of superconducting devices, and most of these devices that are actually being studied and have applications are based on metallic superconducting devices, right? So from the examples that I had given in the previous slide of qubits, superconducting quantum interference devices, QIDs, they're based on Josephson junctions, and often most of these Josephson junctions are metallic, and often they are based on this kind of aluminum technology, so just evaporating an aluminum and then oxidizing and evaporating another aluminum contact. They're great elements, these Josephson junctions, because the fabrication is somewhat reliable and scalable up to a certain point. That's why we're seeing now processes with hundreds of qubits, etc. This is due to having a very good stable oxide barrier, which is the aluminum oxide. And so this can be scaled up to a certain point and lead to applications. And that's very nice. And the physics of these circuit elements is quite well known and is described by this Josephson effect. So it has what we would call a sinusoidal current phase relation. And so in summary, they're really nice devices, and they work, and they're leading to applications. Now, in my talk, I will be talking about hybrid superconducting devices. And first, I would like to address why are they interesting, right? So over here, I think we can think of some practical aspects and some fundamental aspects. And there are some key differences from the start. So this kind of hybrid systems, on the one hand, they already deviate from this behavior from regular or conventional aluminum Josephson junctions, in the sense that the Josephson physics there is governed by, it's a bit different, right? It's governed by Andreev bound states. You can have non-conventional current phase relations, etc. On the other hand, when we think about different material combinations, for instance, superconductors combined with semiconductors, this also opens the possibilities for having more flexibility. So for instance, if we have this kind of hybrid structures, one can have electrostatic tunability by means of gating, and this also allows to control then the Josephson physics. We can then access a physics of a few modes, and where we control transparencies, etc. So, as said, there are practical sides that maybe one can gain tunability, but also fundamentally, it's different and interesting for us, right, as condensed matter physicists. And finally, the final difference here and interesting thing that motivates us is also the possibility to study proximity effects. So here, by combining different materials with superconductivity, one can then study the interplay between, for instance, superconductivity and other properties like spin-orbit interaction or magnetism. And this can lead to new phases, like what have been studied a lot in the past decades, right? Topological superconductivity or unconventional superconductivity. So I hope with this I have convinced, well, I know that many of you work with these kind of topics, so that, well, going to this kind of hybrid platforms is very interesting, and it opens up many different possibilities of exploration. And this is the kind of systems that we are interested to work with. So in this slide I put here the material platforms that we have been focusing on, and also the techniques that we use in my group. So as material platforms, historically we have worked with hybrid superconductor, semiconductor, nanostructures. And most specifically, historically we have been working a lot with nanowires. And I will give some reasons for that. Recently we have also been working with kind of 2D semiconductors that are grown by the group of Autónoma here. And as a parallel line of research in my group a few years, we also started playing with van der Waals materials, but superconducting devices based on van der Waals materials. I will also get into more detail on these material platforms later. But in terms of techniques, what we do, well, we work with devices. So we will fabricate these devices, and we study them. Well, historically, also my expertise comes from electronic transport, as was already mentioned. So we do low temperature quantum transport measurements. But also recently, we have been implementing the capability to study or to apply microwave techniques. So in particular, circuit quantum electrodynamic techniques that are used to study quantum devices. And here today, I will also mention a bit of this on these developments. Particularly here today, I have divided my talk in 3 parts, or there are 3 different topics I will cover. And this is, as I mentioned before, as an attempt to showcase a bit of the recent activities in my group. So I will try not to extend myself too much on any of the topics, so that the talk is not too long. But I will cover 3 representative things that are a bit different that we have been doing. So on the first part, I will talk about some of the work we're doing with nanowire devices. And as I said before, this was the main line of research in my group. In particular here today, I will talk about some proximity effects, and in particular, the inverse proximity effect in these devices. The second part, then, I will focus on some superconducting heterostructures done with van der Waals materials. and in particular, an interplay here of proximity effects of superconductivity and magnetism. And finally, to finish the talk, I will show a bit of how our progress on implementing these microwave techniques to study quantum devices has been going. So the first part here on superconducting nanowires, this I'll mention that it was primarily the work of 3 PhD students, Gabriel, Nacho, and Mario. And for this work, we have used material from Copenhagen, so they wrote these nanowires, they sent it to us. And well, part of the theory was done here by Gorm and Ramon, and also with the collaboration of Alfredo in my department. So the idea here, first I want to make a very brief introduction to these kind of structures. And I think, again, many of you work with this topic over this institute. And others, I guess, have followed the progress in this field in the past decade. But there has been a lot of interest on this kind of hybrid superconductor, semiconductor nanostructures because, well, due to various possible applications, but possibly what has really driven the field in the past 2 decades was the prospects of realizing a topological superconducting phase due to the combination of superconductivity, spin-orbit interaction, and spin polarization that can be in principle achieved in these materials. But there are also other types of applications, right, that people have studied over the course of years, including the possibility of making these hybrid superconducting qubits, which try to combine the best of both platforms, semiconductors, bring it to tunability, and then superconducting qubits, which is a technology that works. So there has been a lot of activity in this kind of materials, but working on the field as well, we have realized that actually this system is so rich that there are many effects that one can always keep on finding and understanding better about the system. So in the past year, since I set up the lab here with my group, we have studied a few of these different systems or effects that have surprised us. For instance, we have studied kind of heating effects that appear in these systems that had been completely overlooked in these hybrid superconductor semiconductor systems, which I will not talk about today. And another effect that had been overlooked by the entire community was an effect which is very simple, but has a very profound effect, which is the inverse proximity effect. Okay? So the wires I'm talking about, they are a semiconductor, so particular indium arsenide, and they're covered by a superconducting layer. Okay? And typically, when we do transport experiments or when we make any device, we will have to contact these nanostructures with some kind of electrical contact. Many of the studies that have been done in this kind of nanowires, and there have been many, use normal contacts or gold typically to contact these nanowires. Well, up to I think our work, people and us included have completely overlooked the fact of what happens at this interface. So is there any kind of impact of the normal contacts on the superconducting properties of this nanostructure? This is an interesting work, and one of the works that actually motivated us to study a bit of this physics from the Copenhagen group, where they studied the superconducting properties of this hybrid material. And the nanowire, in this case, is fully covered by the superconducting shell, which leads to interesting physics, namely when one applies a magnetic field or magnetic flux perpendicular to this wire cross-section, one sees a modulation of the critical temperature of the superconductor due to the quantization of fluxoid. So this is known as the little Parks effect. And in this work, in particular, what they see is that by tuning this superconductor with the magnetic flux, they observe that there is some transition of some sort in which now this hybrid structure can be in the normal state when apply magnetic flux and fully suppressing the superconductivity of the shell. It can be superconducting when we are having an integer number of magnetic flux, but also in some conditions they observe some behavior in which the superconducting transition starts, but the resistance doesn't go to zero and saturates to a finite value. This is also a phenomena that is seen in other systems and is kind of known as an anomalous metallic phase, right? So this is one of this work on these wires. We started studying exactly this kind of geometry, and we observed something quite interesting. Well, essentially, we went back to the basics and tried to be a bit more quantitative. And we realized that the community in general is not very quantitative, and we weren't either. So we were not taking so much, we hadn't noticed this before. But the fact is that this is a superconducting nanowire, and the critical current that this wire can carry is limited by different effects, but normally in absence of perturbations, it will be limited by thermodynamics, so it will be the pair breaking current that you can run. And this can be described by theory. Now, when we compare this to experimental results, what one can see is that the experimental results of the critical current of these wires is much lower than what one would expect from theory. And it doesn't seem to correlate at all with, because this essentially depends on dimensions or geometric factors, apart from the type of superconductor. There's absolutely no correlation. This is from the work I showed in the previous slide, but other works as well. So more or less these wires comes from field groups in the world, and all of them suffer from the fact that the critical currents are much lower than one would expect. So we tried to study this, and we observed a very strong effect of the type of electrical leads that we use to contact the wire. So we did an experiment, as I said, we used the same geometry as in the previous paper I had mentioned, with the difference here that we studied the impact of the electrical leads. So we studied devices which had normal electrical leads and devices which had superconducting leads. The measurement, this is our transfer measurement, so we're measuring the resistance of the wire. And when we characterized both types of devices, we saw a very strong impact of the type of the electrical contacts, as I mentioned before. So if we measure with gold contacts, as was done in the previous paper, we also see that our critical currents are much lower than the one expected from pair breaking. But when we study similar devices now with superconducting contacts, we see that what we measure, the critical current really is comparable or almost the same as one would expect from theory. This pointed to, as said, a strong impact from electrical leads, and we speculated this was due to the inverse proximity effect, so inverse proximity that normal electrical lead would impose on the superconducting aluminum. And this can be more dramatically seen if we plot now line cuts. So this is done here over zero magnetic field, and we see like this very huge discrepancy of the critical current of one wire or the other. But then when we take another line cut at a finer magnetic field, now at over here, they are similar. So what has happened here? Well, the critical field of our superconducting contacts is of the order of a few 10 millitesla. So up to from the fields larger than this 35 millitesla, which is shown here by this dashed line, these aluminum contacts that we deposit are also normal. So when the superconducting contacts turn normal, we also see that this inverse proximity effect takes place. Okay, so that's the idea. It's a kind of a simple thing, and actually, one would wonder, like, why not to expect this? But indeed, as I said before, this was not. This was completely overlooked. So we kept on testing this trying to interpret our results more deeply. And we see there's actually quite interesting physics that takes place over here. And we see, when we start, we try to study really this kind of superconducting to normal transitions more carefully. We see many observations that we cannot, they're not so intuitive at first. But at the end of the day, we can really understand now fully how this transition from the superconducting state to the normal state takes place and how the inverse proximity effect contributes to it. So very shortly here, so I don't take too much long in this part, what we study here, is then how this, the switching current now is changing as we try to weaken the superconductivity by applying magnetic fields, and we then observe really that the physics of this transition in devices like this is really dominated by this inverse proximity effect and then by heating effects that are related when parts of this nanowire turn normal. Okay, so we kind of understand this quite well. I will just go a bit quickly over here. I don't want to extend myself too much, but overall, what we observe is that this wire can have different phases, right? So when we have the normal contact deposited on the superconductor, we will create a local weak spot due to inverse proximity effect. And, and when we start ramping the current, the first part of the wire that will turn normal is this weak spot. And then two different things can happen. First, if once we generate this normal spot, it has a resistance, so when we're running current, this normal spot will start dissipating heat. So if my normal spot dissipates more heat than I can dissipate with my device, this leads to what we call a thermal runaway. So as soon as this normal region nucleates, it will expand and make the transition the whole wire to the normal state. But in other conditions, when the critical current is lower, so this heat dissipated by the normal spot will be lower than what can be dissipated by the device, and we stabilize a normal phase. Okay, and this is actually, we understand now, it lies at the origin of this anomalous metallic phase. So when we can control now we suppress the superconductivity of the wire with magnetic fields, we can generate then a weak spot that doesn't dissipate as much heat, and this is what actually leads to this anomalous metallic phase I had mentioned before. Okay. Okay, this is a mechanism that we have uncovered on this kind of device. So this work now we have in a manuscript in the archive. So, but the one thing I want to mention here, the one thing I wanted to mention here is that this work continues. There are interesting things that take place. Okay, so here I was talking essentially also superconducting nanowire, which is connected to a normal metal, and due to inverse proximity effect, this creates some kind of weakening. And essentially, in a way, we also uncovered a way that, let's say, a way to create a weak link in a superconducting nanowire. Okay, so essentially, when I can suppress the superconductivity here of a superconducting wire, the question is here: when does this superconducting wire stop behaving as a superconducting wire and starts behaving as a Josephson junction? And we believe now, by exploring the parameter space of the system, is that by weakening this overall superconductivity of the wire, we can get to a regime in which we have crossed this threshold, and we create this kind of a weakening. So this is ongoing work. I just wanted to mention this is ongoing work, and we can demonstrate the formation of this kind of weak link physics by doing experiments now using microwaves. and we observe this formation of Shapiro steps in some parameter space. So essentially, exactly when we are able to, in this region where we can create this weak spot that we observe by transport, we see that Shapiro steps emerge from these kind of regions. And we can control this now by means of magnetic fields and which region the system will behave as a weak spot. So this is ongoing work that we're doing in the group, and the idea here is that if we can make really kind of a S and S junction, really by inverse proximity in these wires, so by depositing a normal metal and weakening the superconductivity of this wire, then we can actually create a controllable and tunable weak link that we can play then perhaps to do also quantum devices. And in this area of the research of the lab, I also mentioned, well, we have done a lot of experiments as well in different geometries. Here also by removing part of the aluminum shell, we actually get a semiconductor Josephson junction. And we have been studying this in past years, so also how this behaves with little parks effect. And this is a work we're doing in collaboration now with these people, Carlos, Pablo, Ramon, and Elsa. So at this point, I will actually switch gear completely and also tell a bit of the activities we're doing in terms of 2D materials. This is also some recent work we have published, and this was the PhD, is work from the PhD of Celia, so she's the main person in this work. This was done in collaboration with people from University of Constance, which have helped us in preparing the samples. And, well, theory also done partly over here with Ruben. What is the motivation here of this part? So as I said, historically, our group has worked with this kind of semiconductor, superconductor nanostructures, and part of the big motivation to work with this was maybe trying to access this topological phase, which would arise due to combination of superconductivity, spin-orbit interaction, and magnetism in some way. It turns out that working with these nanowires is very difficult, and that's the reason why in the community we have been working with this for over 10 years or 15 years with often unconclusive experimental results, because there's always disorder and things like this. So in this part, actually, of the 2D materials, we asked ourselves a few years ago whether there would be different systems in which we could get the combination of these ingredients, superconductivity, magnetism, etc., and that could be more robust in terms of getting a topological phase. At that time, we saw this work in which they have used niobium selenide as a superconductor, and then they have grown a ferromagnetic material. This is chromium tribromide. So this is all done in ultra-high vacuum environment. And then they do an STM experiment. And essentially with STM, they can go to these islands here, which are magnetic, but they're in proximity to a superconductor. And they do a scanning tunneling spectroscopy. And they see zero bias peaks, which then they conclude this is due to topology. So in our community with wires, we have been discussing zero bias peaks for over a decade. So one wonders, okay, is this topological? And when we saw this work, we're like, okay, could we do kind of transport experiments on a similar system and maybe try to extract more information than just a zero bias peak? Okay, so that was the motivation of the work, or how we got started working on this kind of systems, heterostructures with superconductors and magnetic materials. So Celia, at the time, with her, we were like, okay, let's try then to make some similar structure, but on a device that we can measure transport. Turns out, 2D ferromagnets are very sensitive to air. And when she was trying to do this, then they were oxidizing, and we're not getting much further of where we wanted to go. But also there are other materials, and okay, so here's an example of work from our collaborators, Ignacio, Ruben, and Pablo, where they also study, okay, well, let's also look at antiferromagnetic textures combined with superconductivity, and they also find here some conditions in which you can get topological superconductivity. And the experimental work that we did, indeed, was kind of trying to implement this kind of systems in which we have a superconductor combined with an antiferromagnet. So, as an antiferromagnet, what we use here is this material NiPS₃. And why this material? Well, this is an antiferromagnet that has the antiferromagnetic texture in the plane of the layered material. So this means we can actually transfer this antiferromagnetic texture to a device. So many of the antiferromagnet to layered materials actually have the antiferromagnetic coupling from layer to layer. So this wouldn't allow us to test this kind of texture on the superconductivity. We did this then with this material NiPS₃, which is also a lot more stable than the ferromagnetic materials we tried before. The samples were prepared in inert atmosphere. So then that's how we got in contact with these people in Constance when we're discussing different materials. They had this material, they have a glove box, so my student went there, she prepared these devices. And the devices essentially are kind of like a sandwich, right? So we use as superconductors niobindicyanide, and we sandwich between two niobindicyanide layers and one layer of this NiPS₃. And we studied. Are we getting to topology? Okay, that's not the point. I mean, we wanted to see what emerges from this combination of the interplay of the superconductivity and this antiferromagnetic texture. I just flashed before, since we changed completely gears, some of the works that are in the literature or had been in the literature on Josephson junctions based on this niobindicyanide. So there has been some works that try different combinations of materials. It all started with this work in which just putting two layers of niobindicyanide, they're sufficiently decoupled that they behave as a Josephson junction. But then people tried putting a graphene in between, or different correlated materials, or ferromagnetic materials. So people had tried different combinations here. To later compare to our results, I just wanted to flash also like a typical characterization measurement that we do with Josephson junctions, right? Which is then to apply a magnetic field perpendicular to the flow of the supercurrent and see the interference pattern. So usually in a Josephson junction that you have a homogeneous distribution of supercurrent, you would get some kind of pattern that is known as a Fraunhofer pattern, right? Which looks something like this, or a bit distorted in other cases, but more or less all of these different devices show more or less this kind of pattern. So moving on to moving back to our device. So this is how it really looks in an optical microscope. So we have these three sandwiched layers, and the Josephson junction forms here where the three layers intersect, which I'm highlighting here in red. And to prevent further degradation materials, then we encapsulate the whole thing with a top HBN layer. So going to the measurements, well, when we measure these at low temperatures, we see supercurrent, so we see a Josephson effect. Great. We see that the supercurrent is not very high, and that's the reason why it's suppressed at temperatures which are lower than the critical temperature of the leads. But that's fine. We're already happy we measure a supercurrent. Now, we apply a magnetic field to do the test that I mentioned before. So see, is this supercurrent distribution homogeneous? And also from these oscillations, one can infer geometrical, the geometrical dimensions of the junction. So we do a measurement like that, and we apply a magnetic field perpendicular then to the flow of the supercurrent. And what we see is a quite different pattern, actually, a pattern that really resembles a superconducting quantum interference device. So to get a pattern like this, essentially what you need is that the supercurrent runs through two separated channels. And now when we apply magnetic flux, the interference will lead to this kind of oscillations. What is striking, I think, about this measurement is how clean and regular the discrete oscillations look. Now, the period of the oscillations, as I mentioned before, has some information about the size of the junction. And when we take into account what is the period of the oscillations and we compare to the device, it is consistent with the geometries that we have. So going back to this photo, the junction has a few microns extension in laterally, and the thickness is the thickness of the field layer NiPS₃, which will be of the order of 10 nanometers or less. So from the oscillations, we get something, an area consistent of 10 nanometers thickness and a width of around 1 micron or a bit more. So this seems to fit what we, the dimensions of our device, but it shows its squid oscillations instead of what we would expect, perhaps a Fraunhofer. Okay? We studied this more carefully, because then we thought, okay, we have some kind of localized channels here, and of course we think, okay, could this be topological, etc. Now, what we did is then, okay, since our experimental setup allows, we have a vector magnetic field, so we can actually rotate this magnetic field over the plane of the junction. So here it's applied over a certain direction, but we could apply by varying and trying to scan where these localized states are. And this is the measurement that we did. So this is over this plane of the junction. And we observe that essentially the oscillations, they follow this kind of parallel diagonal lines. Just to explain, what I'm plotting here is the zero bias resistance, which is what I plot over here of the same measurement. As you can see, when the supercurrent goes at the lowest value, then we see a peak in the resistance, okay, because of the fact that the supercurrent is low compared to temperature, we see a small resistance over there. So following these peaks, we can then follow how the oscillations vary as a function of the angle of the field. And essentially here, this is what is telling us is that we indeed have two localized states. So when we have these two localized states and we're completely perpendicular, when the magnetic field is completely perpendicular to this plane, is essentially when we're perpendicular to these diagonal lines. And when we're parallel to diagonal lines, it would be like when we are applying the magnetic field and not really threading the area between the two loops, because they form a line. And indeed, when we take a measurement along these lines, we don't see oscillations. Okay? So it seems that we have truly two localized states. And when we do kind of a Fourier transform, okay, again, we see that it's consistent with the dimensions of our sample. And the width of these localized states is very narrow. It's below 100 nanometers, maybe below 15 nanometers. So they're truly localized in a sample that is maybe 5 to 10 micrometer, have 5 to 10 micrometer lateral dimensions. We have like two localized states that have maybe an extension of 50 nanometers. And that's it. This is what carries the transport in this device. Well, to us, highly unexpected. And well, as experimentalists, we don't have an explanation for this. So we contact our theory friends over there, and they have this model in which really these kind of localized states, they appear due to the interplay of superconductivity and the antiferromagnetic texture. The thing is that when we place this niobium diselenide on top of this antiferromagnetic structure, well, the edges, and I want to stress, these are not physical edges of the antiferromagnetic material. Our device is as drawn here, so we have an niobium diselenide, but the flake extends. But really at this interface, there will be some kind of uncompensated magnetic moments because they're not perfectly aligned. And these uncompensated magnetic moments actually start giving rise to localized states in this heterostructure. So we believe that indeed what we're seeing is an interplay between this magnetic, antiferromagnetic texture and the superconductivity. Is it topological? there's no way of knowing. I mean, we're just measuring transfer. We can tell where it is, or we can infer or where it is. And from the model, well, this model doesn't take into account all the ingredients to get topology, but also our theory friends say, well, they could put all the ingredients and they would also get this kind of localized states. So it's unsure and has to be tested further, in other words. But from an experimental point of view, we find that the response is very beautiful. We get like these beautiful squid oscillations. Up to 1 Tesla, they're pretty much very regular. Starting from 1 Tesla, then you start seeing kind of first the amplitude goes up, and then goes down, and there are more jumps. So we think here that, well, it is an antiferromagnetic material, so the magnetic susceptibility is low at low magnetic fields, but when you start applying really high fields, one can start having spin canting, and so at sufficiently high fields, one would expect even to have spin flop transitions. So maybe at higher fields here, one has to take into account changes to the magnetization of the flake, which we don't take into account right now. So this is a preliminary, or the first measurements that we have taken. And the results are summarized in this paper that we've published recently this year. But there's a lot of things that we don't know about the system. So clearly we have to study this system further. There are really interesting things that I think come out of the system. And for instance, some measurements we have taken, we also have taken Shapiro patterns of this device, which don't follow really conventional integer Shapiro pattern that one would expect, show some kind of weird fractional behavior to be studied further. So right now what we need is really to have more devices. Turns out that preparing, I mean, I'm not so experienced, well, I'm not experienced into the materials, but it turns out really that preparing these devices is quite troublesome, and it requires making a lot of samples. So that's where we are right now. We want to make more samples to really study this physics in more detail. It seems it's very rich. Okay. To finish, and this will be very quick, it's kind of an update, as I said, in terms of our efforts in the past years to implement microwave techniques to study quantum devices. And this has been the PhD work of one student, Nacho. He has really implemented and worked from implementing this microwave setup from scratch, and also then trying to study our first qubit. The idea here was, again, when he started the PhD, we had the fridge, but we didn't have the know-how and we didn't have the microwave equipment or setup. So the first years, that's what he has worked on, implementing this setup from scratch. In parallel, we have worked in fabrication. So we collaborated with a group of Alicia Gomez at INTA, at CSIC, as she has experience in working with superconducting circuits. She works a lot with detectors, but also the technology to make these resonators is very similar. So we started collaborating. So the resonators we get from her, and then the rest of the fabrication we do it ourselves. So we place these nanowires and make these Josephson junctions, etc. So this was kind of work in parallel to implement this experiment, make the samples, and see that it works. Exactly because of our lack of experience, we thought, let's start with a qubit design or architecture that is not the hardest one. So we are going to use the most common device or qubit architecture there is, which is the transmon. So we have a transmon. The only difference is that we don't use these aluminum oxide junctions, as I mentioned in the introduction. We use a nanowire with a nanowire junction here. Is it the first qubit of this type? No. So the first gatemons, I forgot another reference here, my fault. But it came from 2 papers that were published back-to-back in PRL in 2015. One from the group of Charlie Marcus in Copenhagen, and one from Delft from the group of Leo De Carlo. So it's not a new geometry, but as said, we didn't know how to do these devices, and we didn't know how to measure these devices. So we thought, let's start with a simple geometry and see where we get. There is a difference of our qubit, known as gatemon, so gate-tunable transmon, compared to previous gatemons in the literature, in the sense that Nacho decided to make it the qubit is very strongly coupled to the resonator. So in fact, the qubit behaves as he had designed, and we reach this so-called ultra-strong coupling regime of light and matter. So this is the main difference of our gatemons compared to previous attempts, but as I said, the architecture itself is not new. But anyways, over the course of times and a lot of trial and error, well, the fabrication eventually worked, and the microwave setup also worked. So he could study then, well, we did this kind of spectroscopy, microwave spectroscopy, and then here we see these avoided crossings, which indeed are avoided crossings due to the hybridization of the qubit and the resonator modes. So we studied this, and indeed, as one would expect for ultra-strongly coupled, so one has to use models that go beyond the more commonly used James Cummings Hamiltonian model for strongly coupled systems, and indeed he has studied this in detail, like how you have to include more terms to try to explain the spectroscopy. As I said, I will go a bit quick in this part, also to finish, but I think these are results that got us very excited, because he also managed then to demonstrate coherent control of this qubit, so he also set up kind of time-resolved measurements in his microwave setup, and was able to demonstrate that this qubit can also operate. We can have coherent control of this qubit. Here, these are Rabi oscillations that he has measured. We have measured the relaxation times of these qubits. Here are Ramsey oscillations from which we extract kind of the coherence times. And interestingly, these are qubits in the ultra-strong coupling limit, so this means they're very strongly hybridized to the resonator, which one would then think, well, maybe then one would be affected by resonator losses, etc. Turns out that in these systems, what we see is that relaxation and coherence times are very comparable to other gatemons in the literature, not in ultra-strong coupling. So it means that, I think from this we also conclude that the bottlenecks in this system is still materials related, it's not really related to the architecture over here. There are things that I have not mentioned because it would take a bit longer, but also we see other manifestations of ultra-strong coupling here in transitions that are dependent on the photon number state. So anyways, all of these results are now being summarized in the manuscript that we intend to submit very soon. But some of the exciting, I think, parts for our group was that this was the first demonstration of a qubit, even though it's not a new type of qubit yet, but it shows that our setup works and the fabrication is working. So this now opens the way to explore different things. Of course, as I will get to in my next slide, we also see some interesting physics of ultra-strong. So even though it's not a new type of qubit, but it has let us access this kind of ultra-strong coupling limit and study a few different interesting things. And also, as I said before, so this was also a successful implementation of a CQED setup, which then opens new avenues for research in my group. And indeed, this is a bit kind of the outlook that we have. So we're studying different types of hybrid systems, and we can now think that we open this new line or new technique in our group, that we can also now start thinking of studying different types of device architectures, or also different types of materials integrated to the superconducting circuits. So some ideas that we had since many years when we were already writing proposals, well, we can also try to use kind of Andreev or Shiba type degrees of freedom in qubits, which people have also been doing since then. Some ideas also to use multi-terminal Josephson junctions. We're working with this material from Paloma, trying to get this kind of multi-terminal junctions. Also integrating 2D materials into the superconducting circuits. There is now some activity, for instance, on niobium diselenide based gate transmons, but we could think of different combinations. So I think the time is good. We have now the main systems running. And I think now the combination of these different systems with these transport and CQED techniques can really lead to interesting experiments. So with this, okay, it's missing a bit of part here at the top. I wanted to thank, first of all, most importantly, the students in the group. So here is an older photo of my group. So basically, the results I've shown have been the work of all of the students. Angel, who's now in Paris. Celia did the 2D work. Gabriel, Nacho, Mario did the thing with the first part I mentioned. Nacho is the main responsible and well, let's say the person who set up the security experiment and demonstrated the first qubit. And now we have a new student, Alberto, who will continue with this qubit part of our group. And all the collaborators here, and well, I also thank you for the attention. And if you have any questions, I'll be happy to address them. Well, the heat dissipation is absent as long as the transport is superconducting. So when we're running supercurrents, it's absent. But as soon as we have any normal spot stabilize or any normal spot forming the wire, this normal spot will start dissipating. So the way we run the experiment is really ramping the current from 0 to a certain value. What I wanted to say there was that with the inverse proximity effect, we have a weak spot in this wire. So we anticipate this weak spot will switch before the rest of the wire. As soon as that weak spot switches, then there will be heat dissipating from there. Now, what happens to the heat is what matters, because if the current at which this spot has if the current in which this this spot becomes normal is high, this means that the Joule power, which will be proportional to the current square, will be high, and this might be more heat dissipating than we can dissipate from the device. If this happens, you cannot stop this transition. So this normal spot will just propagate and turn the whole wire normal. Now, if the weak spot is so weak that now the current that I need to switch to the normal state is low, then it might be that I have enough cooling power. So I stabilize a normal spot, I'm dissipating heat, but it's not enough to drive the whole. And this is what we think is behind this anomalous metallic phase, is that you actually have a segment of the wire that becomes normal, and it's just stable. So you have a stable, normal region in the wire.
This stability depends, you say, on the current that you are applying or geometrical factors. So when can you know when this is going to be enough or not?
So the thing is, over here, we have a cooling power that our device has. Where it comes from, well, I can get into that later. But and this is device specific. Okay, so I have a device. It has a given cooling power, which is not high because we're talking about low temperature. So all heat dissipation mechanisms are suppressed. The parts of the system are superconducting, so they cannot carry heat. But parts are normal, so this is what actually carries the heat out. So then it would depend if the switching current of my weak spot is higher or lower than this cooling. There's a threshold current in which below I have enough cooling power and above I don't. So it depends on where I am. So if the switching current on my weak spot is below, I can stabilize a normal phase. If not, I cannot stabilize. So I have two different possibilities here. Now, we can, and this is, I mean, I just didn't have time to go into it. I saw I was taking too much time. But the thing is, at zero magnetic field, imagine, over here our interpretation is that the current that I need to switch my weak spot is higher than what I can cool. So that's why I have an abrupt superconducting to normal transition. As soon as it becomes normal, it drives the whole wire normal. But I can lower the current that I need to switch this weak spot to the normal by weakening the whole superconductivity of the wire altogether. So applying a magnetic field, I weaken the whole superconductivity of the wire with the field. And then now I get to a regime in which this current is lower than my cooling power, and that's why I see this transition over here.
Very nice.
Yeah.
Do I have a... Yeah, well, I had another question, but...
Is there another question of Elsa? Keeps talking. So Elsa.
Yeah, this was about the last part with the strong coupling regime with the microwave measurement. So my question is very simple. So were you looking for this ultra-strong coupling on purpose? Or is just that it appears in the way you fabricated your device?
The thing for this kind of circuits, one does a lot of simulations before you do the fabrication, because you have to adjust a lot of energy scales. So this transmitter will have a charging energy, and then there's a Josephson energy. So you have to tune it to get into the transmitter regime. So this EJ over EC has to be sufficiently high. So there's a lot of simulation over there. So in a way, as I mentioned, the device behaves as Nacho designed it to behave. Now, why going to the ultra-strong coupling limit? Well, it's true, there is some level of coins or randomness there, one could speak. Well, in the beginning, the thing is when you set up these experiments, how do you test that it's working? You need a working device. There's no way. So you can put a resonator. We could put a resonator and measure, okay, I see the resonator, great. But how do I know, like, okay, my whole setup works. Now I can do pulses and I will measure Rabi or Ramsey, etc. You kind of need a qubit. There's no way. But when we started, we were implementing both things at the same time. So the fabrication was also now fully working. So the first samples that we cooled down, he saw no gate effect. Okay, so we saw the resonator, but by gaining the wire, we saw no effect. So we thought, okay, something's not working. Could be many things, but and likely it was problems with the fabrication of the wire part. But also he thought, okay, maybe the qubit and the resonator are not sufficiently coupled. So he decided, well, I will increase a bit. Turns out this is the first device that worked. So we cooled down maybe 3-4 qubits, or well, in total for his PhD there were 20 samples, which is not so many, because for the other part, the transfer part, we have done more than 400 now. Wow. But for this qubit part, it was like 20 first resonator set, but with wires, maybe he tried 2 or 3 that didn't work. And this worked, and it was in the ultra-strong coupling limit. And then when he started measuring, we saw, well, actually, there's kind of really cool things over here. So he has been measuring the sample. The sample was warmed up yesterday after 2 years in the fridge. So he was playing around a lot with it. Yeah.
Mm-hmm. Thank you.
Yeah. So so the thing is, we are not qubit people. We are actually hybrid people. So it's just that now we are at this intersection that is interesting, and maybe we think, okay, there are gate tunable superconducting circuit elements that we can play with. That's great. So we are this, but of course we are not from the qubit community. Now, this was something that puzzled us a bit in the beginning, which was like, he just made, the coupling is just a capacitor, and he just made like the capacitance higher. So it seems like, okay, this is very straightforward to get to ultra-strong coupling. So why is it so difficult, right? And I guess the answer is just it depends on geometry, because this is this transmon, so this is capacitance coupling. Maybe like other types of inductive coupling, it's harder to get such strong. I don't know, we haven't, but yeah, for our geometry it's straightforward, and he could go even stronger. Now the question is there an advantage to go to even stronger? So up to this point, as we saw, the performance of the qubit is not compromised yet, because it turns out that the qubit itself is not good, right? I mean, this is the material itself. So this, but we're at the limit. So ultra-strong coupling would be this eta, which is G over the frequency of the qubit, higher than 0.1. We're at 0.2, and people have gone to deep ultra-strong. maybe there's interesting things here, but I would say our next qubit will probably not be ultra-strong coupling. So if we want to study different things now the physics of the junction, multi-terminal junction, or there are other wires from Jasper we wanted to try, Andrev physics, etc., then we'll probably try to remove this level of complexity and go to a bit lower coupling. Yeah.
Inductive coupling, so it's more difficult.
Yeah. Yeah. So, yeah.
Any other question?
Well, thank you. Nice talk. I have two questions. One regarding nanowires. I think there's a lot of going to play with the width and thickness of nanowires. You say for instance, for single photon detectors with niobium, right? You can play a lot with the hotspot you create with light. In this case, I don't know in which region you are, because how big is the normal area you're creating, and how can you play with thickness and that stuff?
Yeah. We haven't really looked into this kind of, because I think superconducting detectors, I'm not a specialist on this, but you have like a grid or your pixel, right? You have a point where you have really a meander of the superconducting wire, where you have like a sizable area that you can pick up this photon.
I was also playing with a single nanowire at the beginning of the single photon detectors.
So, because we were looking for a different perspective, not from a photon detection, but I thought, okay, because these wires are very, the dimensions are very small, right? So lengthwise, there may be a few microns, and diameter-wise, 100 nanometers or so. So I thought, well, it's very localized, this stuff, and also, yeah. So we haven't looked at from this perspective. Maybe there are interesting things, but yeah, the weak spot, as far as we know, and we haven't studied this so systematically, but it's really defined by the normal contact we put on it. So I assume we can control it up to a certain point, but we're very limited by the size of the wire from the starting point.
Because that would be also very important regarding the Josephson junction, right? How big the area is.
Yeah.
That's it.
So over here, this is exactly what we're playing with right now, because our idea was like, okay, that would be cool, now that we see this kind of weak spot formation, that if we try to make a Josephson junction and we make the weak link just by weakening the superconductivity locally, this is what we're trying to do. But it's work in progress. So we had some preliminary results that maybe look interesting, but then you're absolutely right. We have to control this distance, and that's where we are at. Actually, we're making devices and we're trying to study this.
Very interesting. And the second question is regarding the bottom valves on antiferromagnetic junctions. I've been always working with Josephson junctions, and I will be quite concerned about how you define your area. I mean, with flakes, you cannot control the area. You have larger flake around, so you can have persistent currents around, and they can contribute and see that kind of localized state.
Right.
Too.
The thing here is that this intermediate layer, the magnetic layer, is insulating. So we have characterized this. So it's not really like you have a charge density. So this is insulating.
All right.
It has a sizable band gap, and we're measuring this at like 10 millikelvin base temperature. So I don't think it's kind of really forming on. Also, the thing is, of course, it's not really forming all around, but it's really forming two spots. Okay, these are two localized spots. When we do this rotation, we can infer that there are really two localized spots. Now, we have measured a few samples because, of course, you see this and you're like, well, could it be by chance? The thing is, with this material combination, we never saw, we see a response that is consistent maybe with two localized channels, sometimes just one, but we don't see kind of extended areas where it conducts. But as I mentioned before, it's very tricky to work with this sample. So my PhD student, I mean, essentially what I tell her is like, can you go and prepare more samples and all the time? Because it's like, okay, you prepare a batch and then you measure, and then like a few of them, they don't work at all, I think, or because these are three layers that are stacked on top of each other. and then you have to have really good contact between each pair. And some, they just don't conduct. There is very high resistance. And so I think we need, I mean, I think for this kind of work, you need really a lot of people preparing. So I'm pushing her, because she's the only one working in the group with this, that she prepares more samples, because I think it would be nice. It has very different behavior, so we would like to study this at more depth.
Absolutely. Actually, I'm wondering how Josephson vortices or apical vortices will be here, right? So it's unknown.
Yeah. So, yeah.
Thank you very much.
Sure.
Any other question, comment? Elsa? No? Okay, so let's go to thanks Eduardo again.